Hello. We are continuing with our series on magnetic effects of electric current. On the previous occasion, we had discussed about the Ørsted's experiment, his observation, and then we've continued with Biot-Savart's law, which gives us the magnetic field intensity at a point due to a current carrying conductor. Basically, we are considering a current carrying wire, and then we had the first application of Biot-Savart's law for a straight conductor carrying current. First we considered the finite length, and then we considered the infinite length, where the length continues uh, along its path. And for finite length also we had considered the case of the field along the perpendicular bisector. Now I'd ended the video with a question, which was this one, and what we are going to discuss is the probably you must have tried the answer, but for now let me try the answer for you. uh, in this case, if we are to calculate the magnetic field intensity at that point at the center, which is at the intersection of the two diagonals of the square of each side A carrying current I in the clockwise sense, then let us consider for this length, the top one, for that the magnetic field at the center, well, the distance from the center uh, at the perpendicular bisector of that wire is going to be a by 2. This length is going to be a by 2 because the total length is a for each side, and this is just the halfway through, so this is going to be a by 2. So the magnetic field intensity in that case, as far as the magnitude is concerned, will be equal to mu naught divided by mu naught I divided by 2 pi a, because this is along the perpendicular bisector, which is this condition, of course. And then we have the uh, sine of the angle, and the sine of the angle in this case, well, the angle in this case that it is subtending is this one. It is going to be this angle as well as this angle. Now both these angles, as you know, this complete angle is 90 degrees, and the half of it is going to be 45 degrees. So this is sine 45 degrees, and that gives me mu naught I divided by 2 pi a, 1 by root 2, that is the value of sine of 45 degrees. And that's not all, we have to obtain it for all the sides. And if you wish to see the vector form of it, then we will be considering the directions. Now as far as the directions are concerned, if you observe closely, if you align your right hand thumb along this wire, so your right hand thumb is along this direction, right? And you curl your fingers, and as you curl your fingers of the right hand, they go like this, and towards the center obviously they will be into the plane. And likewise, if we are continuing with the other side, obviously the other sides will have the same dimensions, because this will be a by 2 as well, and this current that is continuing along the wire is I. So if we are aligning the thumb along this direction of the right hand, then what you will observe is your fingers curl along this direction into the plane again. Similarly, for this case where you have the alignment of your right hand thumb along this direction, along the direction of the arrow, so the magnetic field with the same magnitude is directed into the center. And similarly for this side as well, with the thumb aligned along this direction, the fingers curl along this line, along this direction. So all of them going into the plane, that means all of them will be directed along the same direction. So you are going to end up with B net. So this is B1. B net, as far as the vector form is concerned, will be into the plane and will be the sum of all the vectors B1, B2, B3 and B4, and all of them along the same direction. There's no need to consider the angle now, so they will all be directed along the same direction. So 4 times of what we had obtained for B1, 1 by root 2, that is for the sine 45 in each case that is going to be there, and all will be directed into the plane which is denoted by the cross encircled. And the root, the 2 is going to get cancelled over here, the root 2 is going to get cancelled and end up with root 2 here. So finally we have the value to be equal to root 2 mu naught I divided by pi a, and all of that into the plane. So this is the answer or the solution to the numerical that I had ended with on the previous video. So now let's continue with the portion, the further applications of Biot-Savart's law. So the second application has the determination of the magnetic field at the center of a circular coil carrying current. Now, as far as a circular coil carrying coil is concerned, we send the current in, drive it along a circular path, and leave a very small gap over here for it to come out. Now that gap, this is more or less a circular path, and that gap that you see over here at the bottom, that is negligible. So it is a complete circle. Now this circle has a radius, supposedly say a, and as we have shown the direction of the current to be, it is in the clockwise sense in this case. The point here remains the point that is to be determined, where the field is to be determined, is at the center. So point O is where we want to obtain the magnetic field intensity due to this current carrying coil, and the magnitude of the current is I. We consider a small element to apply the Biot-Savart's law. The element here is dl, and as you know, it is directed along the direction of current. So because it is a circular path, at this point it is directed tangentially, and that means with the position of the point considered, they will always remain at right angles with respect to one another. That means a dl and the position vector a for the point, that means sine theta is always going to be sine 90, because the theta is always the direction between the current element and the position vector of the point. So that is why here every point on the circumference of the circle will be at right angles to the point at the center, to the position vector for the point at the center. So there's a simplified way of approaching, and the Biot-Savart's law can be used quite easily over here. That is, dB is the small magnetic field due to the small element dl, elementary length, mu naught I dl. Sine theta, as you know, is sine 90 over here, which is fixed, and the distance is the square of a. Sine 90 goes to 1, so the net magnetic field intensity is simply the integration over that entire circumference, which is dl integrated from 0 to 2 pi a, which is the circumference of the circle. So we have mu naught I divided by 4 pi a squared multiplied with, finally we are going to end up with 2 pi a without going into the details. Pi's get cancelled, 2 gets cancelled with 4 to give 2. One of the a's can get cancelled, so you're left with mu naught I divided by 2a. this is the value of the magnetic field as far as the magnitude is concerned. Now, as for direction, the magnetic field here will be directed, obviously the value is mu naught I divided by 2a. The value over here, as far as the right hand thumb rule is concerned, or the right hand screw rule is concerned, you can take the cross product from dl through to a, and as you take it along the right hand, you find the field to be directed into the plane in this case. Now there is an easier technique for this as well. Now remember, in the previous case what I had mentioned is that when you are drawing the current along a straight wire, straight conductor, what we observe is that if the point is over here, the field is directed into the plane because we are considering the thumb of the right hand. The right hand thumb is along this direction, that is along the direction of current, and the magnetic field intensity, the direction of the field intensity uh, in this on the right hand side was into the plane. Behind the wire was directed along this direction, and then along this direction on the left hand side, and then along this direction on the right hand side. So you were getting a circular pattern, or the field lines were circular, were circulating or spiraling about the given straight conductor. Here the current is in a circular path, or is spiraling about a given central point, and at the center you have the field to be directed, in this case in the clockwise sense. When the current is in the clockwise sense, the field is directed into the plane. Well, for this, the easier way out is that you consider the direction of the current when it is along a curved path. You consider them to be the curled fingers of your right hand. So this current, or the direction, is the curled fingers of right hand. And so let me write it clearly for you: curled fingers of right hand. And then the direction of the thumb extended gives the direction of the field. Now if you curl your fingers of the right hand along this path, along that path, like that, if you are curling 4 fingers along that path, then the extension of the thumb is going to be into the plane over here. Now had the current been in the opposite sense, that is in the counterclockwise sense, in this direction, now curling your fingers in that sense would have given you the magnetic field out of the plane, which is denoted by the dot encircled instead of the cross encircled. So when the current is along the straight line, the field lines spiral about it. When the current is along the curved line, the field lines are straight. So current straight, field lines spiral, and the current spiraling, or being along a curved path, if the current spirals, the field lines will be straight. It's as simple as that. And how to determine that? All by the right hand rule, not the thumb rule or the curly fingers rule, but altogether the right hand rule, because at one point the spiraling has to be taken by the curling of the fingers. Obviously the fingers are curling, the 4 fingers of the right hand will curl, and the extension of the thumb will be straight and will be giving the axis. So here the magnetic field is along the axis, while in the previous case the current was along the axis. So this is how we can determine the direction of the magnetic field quite easily. Else you always have the backup in the form of the right hand screw rule or the right hand thumb rule, which is for the cross product between two vectors. So that is the basis of all of these things. These are just the way of interpreting things in an easier way rather than going to the uh, exactly the orthodox method. So now we are done with the second application. We'll be discussing an extension of this application in the next part, that is in this video itself, that is the field along the axis of this circular coil that we have considered. But before that, I would like to discuss a special case for this. Now, this is the field when we are considering a single coil. Now, as you know that we can have coils one over the other. So these are n number of coils, and obviously they will be carrying current in the same direction. When they are spiraled or they are coiled along a given axis, they will be carrying current in the same direction. So for each coil, you will be getting the field intensity of mu naught I divided by 2a. So for n number of coils, because they are directed along the same line, so the magnetic field will also be directed along the same direction. So you have the net magnetic field in this case to be equal to B1 for the first coil, then B2 for the second coil. Let this be B1 for the first coil. So, and B3 for the third coil, and so on up to Bn for the nth coil, and each having the same value for the same radius and for the same amount of current. Obviously this is a single coil which has been coiled multiple times for that same radius A. So all you are going to get is n times the magnetic field, which is equal to n times of B1, let us say, and it will be directed along the same direction as well, because B1, B2, B3 all will be along the same line, and that is why we are able to multiply the value n over there. So rearranging it, mu 0 ni divided by 2a. So this is the value, and all will be into the plane for the clockwise direction in the clockwise sense. For the counterclockwise sense, they will be directed out of the plane as I have shown over here. There's another case that we can consider, is that if we are taking a sector of the circular path instead of the complete circle. So if the current is supposedly moving like this, we are considering a sector. So in this case, what we are going to get is that at a point which is lying over here, the coil is this one. The dotted lines are just for denoting the ending of the ending of the coil or ending of the wire, which are subtending a certain angle theta on that point. So the wire is supposedly Mn. So Mn is the wire, and it is having a certain radius A, and it is subtending, this segment is subtending a certain angle theta onto that coil, onto that center. Now for this, we have the magnetic field intensity to be equal to, we'll consider the magnitude for now. The direction, as you can obtain very easily, the direction will be the same in case this is because of this is a part of a clockwise coil, so the direction will be into the plane for sure. But the magnetic field intensity in terms of magnitude will be mu naught I divided by 2a, that is for the whole coil, and the rest is, as far as the angle is concerned, the angle being theta divided by 2 pi if it is in radians, because the total angle is 2 pi radians for the complete circle. So this is theta out of those 2 pi radians if it is in radians, or it will be mu naught I divided by 2a. It will be theta divided by 360 degrees if it is in degrees. As you can very well observe that if in this case it was 60 degrees supposedly, then 60 divided by 360 will give you 1/6 of the total magnetic field that would have been the case for a complete circular coil, whereas this is 1/6 of it. So this is how we deal with the numericals associated with this kind of uh, arrangement of the current flow across a coil of a certain radius or even its sector. Now let's move over to the field along the axis of the circular coil. So here we are obtaining the field at a point along the axis of a current carrying circular coil. So let's see, here we have a circular coil. What I am trying to show you in this figure is that the circular coil is standing upright, and there will be a certain entrance point and an exit point. We need not show that because the distance will be very small, so we are just omitting that, as you have understood in the previous case, so there's no point repeating it. So let the current be along this sense over here, and we are just taking the axis of the coil and considering a point, say the point being P, which is lying at a certain distance, say x, from the center of the coil, the center of the coil being at the point O. Now this is the point P where we want to obtain the net magnetic field intensity due to this entire circular coil. For that we need to consider two segments instead of one, which will make it easier for us. You'll be knowing gradually why we are considering two segments instead of just one segment, which was the case on previous occasions. So this is DL, this is DL as well. In this case, the DL is directed along this direction, coming out of the page that you are viewing right now, because this is in 3 dimension now. So you have to use your imagination over here, and this is going into the page that you are viewing right now. So these two lines, these two elements will obviously impact this point P with a certain magnetic field dB. Now if I was to take the position of the point P with respect to this DL, with the radius of the circular path being A and this distance being x, what we are going to get is, let us take this as r being the position. R is simply equal to the root of the squares, that is x squared plus a squared under root. This is by Pythagoras theorem. Same will be the case for the DL element at the bottom. The distance being r, the position vector of the point will be directed along that line. So this is r vector. X is this one. Now, with r being available to us, we can obtain the direction of the magnetic field intensity due to the top and the bottom elements. The magnetic field intensity due to the top element over there, dl, if you can use your right hand and obtain the and curl your fingers, the right hand screw rule will lead you to dB, which will be along this direction. This is a dB1. Why dB1? Because the directions will be different. And if you can use your right hand for the bottom dl element, and you curl it towards r, then dB2 will be along this direction, which I'm going to indicate by a different ink for your convenience. So dB2 will be along this direction. This will be dB2. And dB1 and dB2, with those values given to us, dB2, with those values available to us, or the expressions. Well, let's see what are the expressions in the first case. dB1, in terms of magnitude, what we see is mu naught I divided by 4 pi. Distance here is r squared, so this is x square plus a square as a whole. Root over of that and squared gives us that same value. And at the top, you have nothing at the top. That's the sign that you get over here is 90 degrees, because again that is along the circumference and this lies along the axis which is passing through the center. So obviously the angle is always going to be 90 degrees. So this is sine 90, which goes to 1. Same will be the case for dB2 as well, because the dimensions are the same. The radius is the same, that is a. The rest of the things, I, mu naught, 4 pi, they are constant. The distance as well from the center is x. So a square plus x square, which would have been the variable over here, that remains constant for dB2 as well. Now, in this case, what we are going to obtain is that we have a dB2 along this direction, we have dB1 along this direction, and both are symmetrical. So along this line, what you are going to find is, just drawing a separate case over here, so the same thing in a separate frame. So we are going to have two components of each of those vectors. So let this angle that we are considering over here, with respect to that line R that we are observing, this is the line R that we had considered. So with respect to that line, we need not be concerned about R. We are concerned about okay, let's see. So this is theta, which R is subtending. So if R is making an angle theta with respect to that axis, now let me give you a three-dimensional view. I'll try to make it simple for you. Now this is a dl, I'm showing the top one, and this is the r vector pointing towards that, and this is that plane of dl and r, out of whose cross product we are getting db along this direction, and it is perpendicular to this plane, isn't it? dB will be perpendicular, because in cross product you have the vectors and the product is perpendicular to the plane containing two vectors. So dB1 that I had shown, that will be perpendicular to this plane containing dl and r. Now this plane is, because as you can see, r is making an angle theta over here, this is the point P, r is making an angle theta over here, so this dB1 must be making an angle theta with something. And what is that thing with which it is making? So this is theta, this is 90 degrees, so this thing has to be 90 minus theta. Take the case of this side over here, that is the vertical line. So this angle has to be theta, because this straight line, which would have been along the axis, that will be making an angle 90 degree with respect to this line. So these lines will be making an angle of 90 degrees with one another. This is 90 minus theta, so this has to be theta, because this is 90 minus 90 plus theta. So this will end up with theta. So that means these two angles, this is theta and this has to be theta as well. So these two angles are theta. And that is why you have dB2 cos theta along this direction and dB1 cos theta along this direction. And both these terms being in opposite sense, dB1 and dB2, as you know, are equal in magnitude. Both these terms with the thetas being same, they will be cancelling out each other. And that is the exact use of taking the diametrically opposite elementary lengths, dl on the top and dl exactly diametrically opposite at the bottom. By taking these diametrically opposite elementary lengths, what we do is we do away with the cosine terms, the cosine components, and make calculation easier. The other term that is going to be there is dB2 sine theta along that line, and similarly dB1 sine theta along that line. And this is for the entire circle, because we will be considering the dl elements as we will be integrating across that circular path. So we'll be integrating for that whole circle, and we'll be getting the cosine components which will be cancelling out each other, while the sine components remaining in the same direction will be added to each other. So the net magnetic field, the elementary magnetic field, that even if you take the vector, they are along the same direction, so they will be added. So the net magnetic field here will be dB1 sine theta plus dB2 sine theta, and as you know, we have the values of dB1 and dB2, and I forgot the dl over here. So mu naught I divided by 4 pi x squared plus a squared, that's all right. And then we have a dl, and then we have the factor 2, because both are the same, dB1 and dB2 both are the same, so we are having the factor 2 for them. Now the net magnetic field therefore will be an integration. We'll take the magnitude for now. So this will be the integration mu naught I divided by the 2 can get cancelled with 4 to give 2, mu naught I divided by 2 pi and x squared plus a squared. And well, the sine theta, the theta, as you can know, we can take the point anywhere we like, and in that case the value of theta keeps on changing. So for that sine theta that we have over here, the sine theta in this case, in the first figure that we have, that is the theta, and the sine theta is going to be the perpendicular, that is the value a, divided by the hypotenuse, that is x squared plus a squared under root. So we can put that value of sine theta over here, putting the a at the top for that sine theta, and the x squared plus a squared under root when multiplied to this will give us 3 by 2, because that is x squared plus a squared, and then x squared plus a squared to the power half is going to end up with x squared plus a squared to the power 3 by 2. I'll rewrite for the denominator part, it's pretty unclear over here. Mu naught I a divided by 2 pi x squared plus a squared whole to the power 3 by 2. And then we have the dl. Now remember, these factors that we are seeing over here, x can change, but in that case, if we had mentioned theta, we would have had two variables. We would have, in case x would have changed, theta would have changed as well, but we do not want that for integration purpose. So we needed to restrict it to one variable, which can be chosen as far as our convenience goes. So x squared plus a squared to the power 3 by 2 dl is integrated. Now dl to be integrated here from value 0 to not 2 pi a but pi a, because we have two elements over here and for them the factor 2 was already multiplied over here, which got cancelled. So finally what we are going to end up with is mu naught I a divided by 2 pi, and we have x squared plus a squared to the power 3 by 2, and then at the top we will have a pi a out of that integration. The pi's can get cancelled out. We end up with mu naught I divided by 2 x squared plus a squared to the power 3 by 2, and this is a squared. This formula looks pretty horrible, but it's easy to remember when we study a case of it. Well, in this case, this direction is, as you can see, all were directed along the axis. So they were going towards the left of the axis. And if you remember the previous case where we had dealt with a circular coil carrying current, the clockwise was showing into the plane and the counterclockwise was showing out of the plane, then you can easily obtain the direction over here, because dB was going into the plane, as you can see, of the coil. Then the coil, as if you align your curling fingers, the four fingers of your right hand along the direction as shown, that is like this, which is the direction of current, then dB, which is the extension of the thumb, is going along this direction, which means the magnetic field is along this direction while the current goes into the plane in this case. So the curling of the current gives the straight direction of the magnetic field over here. Now move over to the other side. If you were to consider the magnetic field on the other side, that I have just drawn the figure again, on the other side, on this side of the coil, the current would have been counterclockwise, and similarly the magnetic field would have been out of the plane, because the magnetic field continues along this direction towards the other side. So the magnetic field enters in this direction and it exits in this direction. Both the cases will be quite complementary to one another, so there's no problem with that. So it is headed towards into the plane on the right hand side and out of the plane on the left hand side, so we need not be concerned about the direction. But as far as the formula is concerned, what we are going to deal with is that if this point was taken and reduced to the center, because the center also forms the part of that axis that we have considered over here. So if this point was to be taken to the center, that is at the point O, then x at center, x would have reduced to 0, because the x completely merges with that the point P merges with that point O, so x goes to 0 in that case. Now in this formula, if x goes to 0, what happens? It will be pretty interesting for you, because mu naught I a squared divided by 2, x has gone to 0, a squared to the power 3 by 2 is going to give you a cube, and a square, when cancels with this, you are left with mu naught I divided by 2a, which is nothing but the case that we had studied right here, this part, mu naught I divided by 2a. So it's easier to remember this formula. You only have an extra x squared over here to the power 3 by 2, and because this x square is going to vanish for the merging at the center, you are going to end up with a cube, and that in order to get this a single a, you need an a square at the top. So if you remember the process, you can remember the formula pretty well. So this is my method of remembering this formula. In case I get confused, I remember it this way. This is the only way that I find useful. If you can come up with some other way that will be handy, you can comment about that as well. So these were some of the applications of the Biot-Savart's law. We'll be discussing a few more things about the magnetic effect of electric current. There are quite a lot of things to discuss, but that will be in the upcoming videos. Till then, thank you for watching.